All right, I think we're rolling. Today we're going to continue talking about caching, and then we're going to move on to one of the most fascinating and oldest computer design principles, and that's virtual memory. Um, our programs and multi-programming environments, as well as our operating systems, heavily rely on virtual memory. And it's a very fascinating topic. So I'm hoping to be able to cover quite a bit of that today. Just as a review, we covered set associative caches last time, and so the problem with direct mapped caches is that they create a large number of conflict misses, and that's because of the very rigid block placement strategy. Now, of course, one of the main advantages to a direct map cache is simplicity. It's just a very simple cache to conceptualize and implement. And so this slide here, just to recap, shows a 8 block cache configured in several different ways, no pun intended, as the associativity goes up. So in a direct mapped cache, um, it's a one-way set associative essentially, and so there's 8 sets because there's 8 blocks, and each set only has one block. Uh, a two-way set associative, okay, has 4 sets, and each set has 2 ways that you can put a block into. Okay, so the way I look at it is there's two ways of storing a block. Okay, and then we move to 4-way set associative, and because we only have 4 blocks, each set has 4 blocks. Because we only have 8 blocks, I'm sorry, each set has 4 blocks. That means we only have 2 sets. Okay, and then the fully associative has essentially just one set. Okay, and each of these caches require a different number of index bits. Okay, so the direct mapped or one way, okay, would require 3 index bits because there's um, 8 sets, and the two-way set associative would require 2 because there's 4 sets, and the 4-way set associative would require 1 because there's 2 sets, and the 8-way set associative or fully associative, which, well, 8-way set associative is essentially fully associative if there's only 8 blocks. Okay, that requires 0 index bits. Okay. Okay. Um, Moving on. So we talked about how we can actually construct set associative caches, and for small number of ways, from like say 2 to 8, we can do so by just combining direct map caches. Okay, so here is a 4-way set associative cache that's constructed using 4 um, direct map caches. Okay. And of course, as we mentioned earlier, we want our placement strategy ensures that we never place a block in um, multiple ways within a given set. Okay, so that way, when we are looking for a block, we know that only one of these comparators, if any, will actually hit. And so whichever one actually hits, then our muxing logic then selects that, and of course our hit signal is an OR of all of these comparator outputs. Okay, and of course each comparator output also looks at the valid bit. Okay, and now if none of them hit, then the main hit signal down here will be 0, which means it's a miss, and then the cache controller will go out and replace that particular, or we'll go out and retrieve that particular block. Okay. So we talked about some advantages and disadvantages. Pipelining becomes a little more difficult, and we increase the hit time. Okay, because there's more comparison logic, right? If we go back to this diagram, we have a lot more logic here than we did with the direct map cache. Now, of course, all of these comparisons will happen in parallel. So, but then we have all of this muxing logic and whatnot. Okay, so it increases our access time. Okay, the other thing it does is it increases the energy consumption per access. Okay, and so that's because in the prior direct mapped case, we're really accessing you know one piece of data. Okay, but in this particular case, now we're accessing 4 pieces of data, and only one of them will be used, and the others will be discarded. Now, I want to say though that the overall energy of the system is not necessarily increased when using set associative caches, and there's a couple of reasons for that. For one, we could actually um, optimize this cache by only accessing the tag portion of each of these caches, okay? And then after we've done the comparison, then we can go ahead and access the data, okay? So if we do that, we'll actually save a considerable amount of energy, and actually in that case, a set associative cache may actually be more energy efficient, okay? So we can't just immediately say that set associative caches consume more energy. They tend to consume a little bit more energy per access, okay? But that's not always the case, depending on how it's configured. And also, overall, even though the set associative cache may consume more energy per access, okay, it may actually reduce the energy consumption of the overall system, which, of course, that's ultimately the goal. And the reason it does that, or potentially could do that, is because it reduces the miss rate, okay, which reduces the amount of time the microprocessor is just idle doing nothing. So it improves set associative cache by reducing conflict misses, could in fact actually improve the efficiency of our processor and ultimately make it more energy efficient. And so there's again a lot of different knobs we can turn here, and so and I've got some graphs that I believe I have some graphs here that show where you get the most bang for your buck. And the spoiler alert is, yeah, I've got a little table here. The spoiler alert is that you see the most improvement going from direct mapped to two-way set associative. Okay, so this little table here shows that going from direct map to two-way set associative, we get a 15% decrease in misses, and that's all because of reduction in conflict misses. Okay, and but then we see that going from two-way to four-way and eight-way, or four-way to eight-way, we don't see that drastic of an improvement. Okay. Now, the one thing I want to point out though is this doesn't sound like a whole hell of a lot of improvement, but the reason for that is because this is a pretty large cache. Okay, this is a 64 kilobyte cache. Now, granted, it is using the Spec 2000. This is, by the way, the cache that we looked at earlier in the lectures, the Intrinsity fast math processor. So we looked at its cache. Well, so this is a 64 kilobyte cache, and if we were to reduce that cache to say 8 kilobytes, we would see a much more dramatic improvement because of associativity. So interestingly enough, okay, increasing the cache size decreases the uh, miss rate, okay, and increasing the associativity decreases the miss rate. So we could actually increase the associativity in lieu of increasing the actual size of the cache. Okay, so again, these are trade-offs. Okay, and by keeping the cache small, okay, we could have a higher associative cache that's smaller, okay, and that would allow us to keep the access time still pretty small, okay, which means we can run at the speed of the processor. This is obviously a level 1 cache right here. Um, so there's a lot of trade-offs, okay, when building a cache. And the other thing is you may find that adding more associativity uh, has some other advantages, and we'll see that in when it comes to virtual memory. Is in processors that support virtual memory, a lot of times they add more associativity just to make the virtual memory system a little easier. Okay, and that was what the R4000 did. And so even though they don't need the higher amount of associativity, it makes virtual memory easier. And once we talk about virtual memory, you'll kind of understand why. And then as a result, you decrease your miss rate, and so then you can actually even have a smaller cache. Okay. Okay. So I wanted to work through a quick example in the book to kind of look at how associativity essentially can improve the situation. Okay, I find that if we do an example, we can set this a little bit more in stone in your mind. Okay, so what we're going to do is we're going to look at a um, 4-entry cache. Okay, so this is very basic, and we're going to look at a 4-entry cache. So four cache blocks. We're going to look at it assuming direct map, um, two-way set associative, and fully associative. Okay, and we're going to go ahead and look at it with the following accesses, where we have 0, 8, 0, and 6. Okay. Okay. I don't know. That looks like a sigma more than anything. Okay. All right. So let's start with the direct map cache, and we're going to look at the contents. We're gonna draw a little table here. Okay. So we're going to say memory access. Memory access. Okay, whoops, and I'm always back myself into a corner here. Okay, and then we're going to go ahead and we're going to define whether it's a hit or a miss. Okay, I'll just put a hit here. And then we want to put the contents. Okay, so we're going to have set, hold on here. It's a lot easier to erase here. So set 0, set 1, set 2, and set 3. Okay, because this is a direct map cache. Okay, each of our blocks, we only have one block per set. Okay, all right. So the order of the access is 0, 8, 0, and 6. Okay, and we want to look at so when we have the first access, okay, we have a 0, and of course our cache has nothing in it. Okay, time goes down. Okay, in this particular example. Okay, this is time going down this way. So the very first access, there's nothing in our cache. So this is a miss. Okay, and so then after that, of course, then we'll go ahead and we'll access location 0, and we'll put it here. Okay. Well, why do we know it goes here? Well, we want to look at the lower bits of our um, address, which is 0. Okay. So then it has to go into set 0. This particular example assumes block offset, and so in other words, each cache block stores only one word. Okay, so you could either think of it that way, or you can just think of these are cache block uh, addresses. Okay, and of course we know in a real cache system there's a block offset because each block has multiple words, and then there is a byte offset because each word has multiple bytes, and our addresses are byte addressable. So this is a toy example, but it'll get the point across. So you can think of these as block numbers almost. Okay. Okay. So 0. Then the next one, when we have 8, well, essentially, um, 8 mod 4 is 0. So where is this going to go? Well, it's going to go in set 0. That's where it's supposed to go. So this is going to be a miss. Again, now this is a conflict miss. And then after this access, we basically replace block 0 with block 8. Okay. All right. And then we have another access to 0. Well, now look at this. Okay. We're actually conflicting. So now we're going to evict. Okay, we're going to evict block 8 and put block 0 back in there. Okay. Okay, and then finally we have 6. Okay, and that's going to be a miss. So what set does 6 map to in this example? Well, it maps to set 2. Okay, and so it's a miss because if we go to set 2, it's empty. Okay. And then after this, we're going to have 6 in here. Okay. Okay, that's the direct map. So let's add a little bit of associativity. Okay. So again, we're accessing 0, 8, 0. Whoops, what the hell did I do there? 0, 6. Okay. Now, because it's set associative, that two-way set associative, we have fewer sets now. Okay. So again, we have mem access. Okay. And we have hit or miss. And then now we have our sets. And then within each set, we actually have we have 2 blocks. So we have set 0 and set 1 and oh, well, and that's it. Yeah, just the 2 sets. So let's see here. We need to give ourselves a little bit of space. Okay. Set 0, set 1, and then we'll divide this out. And then what we're going to do is we're going to put a dividing line here. Okay, and then another one here, and another one here, because we still have 4 blocks. Okay, we have 2 sets, and each set has 2 blocks. Okay, so now when we look at 0 well, 0, but in general, when we look at our block address here, we now mod to that address to then figure out which set it fits in. And by the way, your homework, which I released yesterday, I believe, was it yesterday? I think it was yesterday, or maybe the day before, has you go through an example like this. Okay, so it'll be very similar to this, and you have a number of accesses that you have to do, and so so this is kind of should help you out for your homework. Okay, so when we have 0, well, 0 mod 2 is 0. Now, of course, so that means we go in here in set 0 is where this particular block can go. There's nothing in the cache, so it's a miss because that's a compulsory miss because there's nothing there. Okay, And we'll just go ahead and stick it here. But honestly, it doesn't matter where it goes, which one of these sets. It can go in either one of these two sets, okay? Okay, so then the next access we're going to have is 8, okay? Now, 8's going to be a miss, okay, because we look at our set 0. Well, first of all, we take 8 and we mod to that 8. We mod to 8, okay, and we get 0. That tells us that 8 is going to go in the 0 set, okay? Now, we look in the 0 set, and there's already block 0, but that's not what we're looking for. We're looking for block 8. So it's not there, so then we basically have to pull it in. Now, notice I put it in this other set, okay? I'm sorry, I put it in this other block, this other way, okay? Because 0 is already consuming one way, and so then we just simply put it in the other way, okay? And you would have a bit that would you have a valid bit that would indicate that that particular way was available. So we would obviously pick the available way. Okay. All right. Now we're going to go and where x is 0 again. Okay. And of course we know that we take 0 and we run it through our mod 2 calculation, and that tells us that that block has to be located in set 0. Okay. And so then we look in set 0, we do a comparison, and bada bing, bada boom, there it is. So this is a hit, okay, because it's actually there. I don't know if I mentioned this, but in this example, each of these lines is showing the contents, the current contents of the cache. I may not have made that terribly clear. This 0 looks an awful lot like a 6. Okay. All right. Now we're going to have a 6, which should look an awful lot like a 6, hopefully, but probably look more like a 0. And mod 2 of 6 is essentially 0, right? Okay. Well, so what does that mean? Well, that means that we have to evict one of these blocks. Whoops. I just looked here and somehow we did a no-no. We did exactly what I told you our placement strategy is not supposed to do, and that's put duplicate blocks in our sets. And so we don't want that. We don't want sets with duplicate blocks. Okay, so that's supposed to be 8. Okay, so 6 maps into the 0 set, and so the issue that we have here is that that one of these blocks has to be replaced. Now, this brings up another question with set associative caches, or even fully associative caches, is we have to have some sort of replacement strategy. So what should we do here? Well, intuitively it makes sense because caches exploit temporal locality, is to replace the least recently used block. Okay. So in this case, 8 turns out to be the least recently used because we just access 0. And so between 8 and 0, 8 is the least recently used, and 0 is the most recently used. Okay, so that's the one we're going to replace, is 0, because is 8, because that will allow us to exploit the most temporal locality. Okay, so we're going to put 6 in here. Oh man, this is okay. I'm sorry. This is what happens when I do a lecture at like 10 o'clock at night, okay, or whatever time it is. I'm not firing on all cylinders. Okay. Okay, we're going to leave 0 in there. and we're going to replace 8. Sometimes I find when I make mistakes, it may be a little frustrating for you, but I find the students sometimes understand the material a little bit better because they're like waiting to catch me making mistakes, and kind of exciting. Okay, so there we go. We had a miss, and so we had one conflict miss, okay, and 2 compulsory misses, whereas in the previous example we had 2 compulsory misses and 2 conflict misses. Okay. All right. So this before this example gets too boring, let's go ahead and look at the fully associative case. Fully associative case has no sets, or one set basically, I guess. That's the way you could look at it. Okay. And so really we don't even have to label any of these. We just need to make sure there's 4 slots. There we go. There's 4. Okay. So this one's real simple. We don't mod anything because there's no index. Okay. So basically you just put the damn block wherever you want it to go. so so first of all, this is a miss. Okay. Because the cache is empty. So let's just put it here. Why not? We could put it in any one of these slots, but we'll put it just the first one. Okay. Then we're going to access 8. Well, we have to have a comparator per block, and those blocks are going to tell us, yeah, there's nothing with this tag that indicates that 8 is here. So right now mem0 is in. Let me just label these blocks. This is block 0, 1, 2, and 3. Okay. This is your block number, so I can uniquely identify each one. Okay, so block 0 still has 0 in it, and now let's just say we just went in order, so then block 1 will now have 8, and that's a compulsory miss. Okay, now we're going to come back and access 0. That's a hit, because our comparator is going to compare it and say, yeah, it's right here. It's in block 0. Okay, and then we'll retrieve it. Now, block 8 remains in the cache. Okay. And then we're going to access 6, and that is also going to be, oh, no, wait. That's not a hit. What are you talking about? That's not a hit. Okay. It's a miss because it's not in the cache. But we don't have to evict a block. This is really looking nasty. Okay. I think you all get the point at this point. Okay. I made my columns too small. Okay. Whoops. And now I'm gesturing this. 8. And then let's just put it over here so we have space. Plus that'll demonstrate that, hey, this can go in any block. Okay. There you go. Now, if we come back and access 0 or 8 or whatever, they'll still be in the cache. So you would have to actually make this example a little bit longer to really appreciate how this works. Now, of course, your homework will ask you to do that. Okay. Okay. All right. Let's go back to the lecture slide. So hopefully that little example kind of illustrates why um, set associative or how set associative reduces conflict misses. So one of the questions that we now have on with set associative is which block to replace. Okay, so associativity introduces another question, which is when replacing a block within a set, which block should we evict? And again, intuitively, it makes sense to replace the least recently used block so we can continue to exploit the most temporal locality that we can. Okay, so that's one of the most efficient block replacement strategies. Okay, so for your quiz question, define least recently used block strategy. What does that mean? Okay. All right, so least recently used is very easy to keep track of with a two-way set associative cache. You simply have one bit for each set, and so if it's 0, then maybe it says that way 0 is least recently used. If it's 1, then way 1 is least recently used, and then whenever you access um, the cache, if you access way 0, then um, then you flip the bit so that way 0 is not the least recently used. Okay, so you would set that bit. Okay, pointing to way 1 being least recently used, and then if you access way 1, then you clear that bit, saying that, hey, way 0 is actually least recently used. Okay. Then when your cache is accessed and a cache miss is detected, then the cache controller can go and look at that bit to determine which block it's going to evict. Now, if you recall, last time we talked about different write strategies. We talked about write back, write through, and in this particular case, we're looking at we're I'm describing the example as though it's write back because we're evicting blocks. You don't well, you do evict blocks in a write through case as well, but in the write back case, we're going to look at the dirty bit of that block that we're evicting, and if it's set, then we're going to have to actually write that back to the next level of memory or to a write buffer, as we mentioned last time. Okay. Okay. Um, because least recently used becomes more difficult as you move to 4, 8, and so on and so forth ways, we have to have a different strategy. And so there's a couple of popular strategies. One is a pseudo least recently used, and there's actually also FIFO is another one. And then random. Random actually works surprisingly well. Random is just you have a random counter that's going, and when your cache controller decides it needs to evict a block, it just uses that counter to decide which block to evict. It sounds crazy, but it actually works very well. In the graduate class, we actually look at some studies done on block replacement strategies, and we look at graphs, and we look, some data collected using spec benchmarks and whatnot, and from there you can actually see that random doesn't do that much worse, really, than least recently used. So it's kind of one of those things that it almost just makes sense to, if it's a two-way or four-way set associative, it's pretty easy to keep track of least recently used. But past that, well, four-way is a little complicated. Four to eight-way, you'd probably use pseudo, and then anything past that, you would probably just use random. Okay. Okay. Um, So more on implementation of set associative. Anything beyond 8-way becomes more difficult to implement with SRAM and comparators. So we would actually like a different way of doing this. So for example, a fully associative cache is not constructed using multiple direct map caches. Okay. But 2, 4-way, and even 8-way can be easily created using direct map caches. But past that, what we're going to do is we're actually going to use what's called a CAM, or Content Addressable Memory. Okay, and so what we do is we actually we take our SRAM cell, and included in every cell, we go ahead and include a little comparator circuit. Okay, and so that means that we can provide data to this CAM, this content addressable memory, and it will actually use that data. It'll all the comparators within each of the SRAM cells will look at that data and determine whether there's a match. Okay, CAMs are used in the networking world actually for hardware-based firewalls. Okay, very fast firewalling. Okay, so for some high-speed networking equipment that that you might have at the trunks and whatnot, they'll use cams. But we can use a cam for the tag store for a fully associative cache, and then an SRAM for the data. And basically, we take the output of the cam and feed that into the address lines of the SRAM for the data store. And that's actually how you build a fully associative cache. Okay, so again, the tag store is for a fully associative cache is built using a content addressable memory, um, which essentially incorporates a comparator circuit in every SRAM cell. Okay, and then the data for a fully associative cache is still built using traditional SRAM, like we looked at earlier. Okay. Well, that's really about all I have to say um, about fully or associativity rather. Okay, so we talked about various ways. Let's just recap real quick. We talked about various ways of reducing um, our um, our miss rate. Okay, so we can increase the cache size. That will reduce the miss rate. We can increase the associativity. That will reduce the miss rate. Okay, or we can play around with the block size. Okay, um, so increasing the cache size increases rather decreases capacity misses. Okay, the cost of increasing the cache size is of course larger caches are slower, so that affects the hit time. Okay, um, increasing the associativity reduces the amount of conflict misses. Okay, but the downside there is it increases the complexity of the cache and could potentially increase the access time. And of course, we talked about how it may or may not affect the memory or the energy consumption. Now, of course, also a bigger cache will also require more energy to access. Okay, so those are your trade-offs. Maybe the bigger cache will reduce your miss rate, uh, which will which will ultimately bring the efficiency of the processor or the energy cost of the processor down, increasing the efficiency, but it may increase the cost of an individual access. Okay, but that might be a win. Okay, and then increasing the block size decreases compulsory misses and refill cache misses. Okay, and um, but it comes at a cost of increasing the miss penalty. Okay, and if you increase, and the reason it increases the miss penalty is because now you have to transfer more data for every miss. But it the the advantage to increasing the block size is you take advantage of spatial locality. Okay, but then that advantage, you'll reach a point of diminishing return where you actually start increasing your conflict misses by increasing the block size. Okay, so then at some point you're actually going to start increasing your miss rate if you go too large of a block size. Okay, so that's kind of some fun information there. Um, and there's a couple other strategies we can do to improve the performance of our cache. Ultimately, remember the performance of our cache is based on two things. It's based on the miss rate and the miss penalty. Okay, so we talked about a number of things to reduce the miss rate, but then the question is, how do we reduce the miss penalty? Okay, well, one surefire way to decrease the miss penalty is to increase the number of levels. So if you have just a single level cache system, okay, then you can add a level 2 to decrease the miss penalty of the level 1, okay? And I thought I had slides on this. Maybe it's further on. Maybe these are just more advanced caching techniques, but I guess I was getting so excited to go to virtual memory um, that I forgot to make slides for this. But um, and sometimes I mix up what I talk about in the graduate class versus what I talk about in the undergrad class. It's late, so I'm stumbling for words and whatnot. I apologize. This is probably a painful lecture, but hopefully you're at least enjoying the material. Um, okay, so um, one way we can also um, decrease the miss penalty is a technique called critical word first. Okay, so the thing is when we request a particular word in the cache, and it's not in the cache, then we have to invoke a miss. And I had mentioned that increasing the block size can increase the miss penalty because you have to transfer more data, okay, for each miss. But the processor is held up waiting for that requested block. Well, it turns out you can actually access that requested block first from the next level in the memory hierarchy, and then as soon as it comes in, give it to the processor and then let the processor go. And then while the processor it continues executing, the cache controller finishes filling that cache line. Okay, that technique is critical word first, and it just makes intuitive sense, and it's almost always used. I implemented a cache for our processor, and we definitely are using critical word first. It just makes a lot of sense, and it turns out if you remember how we access data. Um, in a memory is you pay a large penalty to access a given row within that memory, and then any word that you want to access in that row, you can access very quickly after you've taken the time to access the entire row. And so that means that we can actually access the words out of order. Okay, so for example, if we have a cache block and cache block, and it has four words in it, 0, 1, 2, and 3. If if 2 is the critical word, so 2 is the word that the processor is actually requesting. I feel I better draw this because it's gonna be really confusing. Okay, that's why I have all these little blank um, pages. So, okay, here's our cache block, and again, our cache block has, well, that's a really crooked line there. Our cache block has four words in it: 0, 1, 2, 3. And let's say 2 is our critical word. Okay, so 2 is the word that our processor is actually requesting. Okay, and after picking out the index and everything, then it realizes, oh, it needs to go in this particular location. Okay, so I don't know, this could be index 53. I don't know, just making stuff up here. Okay. Well, then what we can do is we have to transfer four words to fill this cache block because this cache block has four words. But we can actually go ahead and access word 2 first. Then we can go ahead and access 3, and then we wrap back around and access 0 and 1. And we do so without any extra penalty because all of these words within this single cache block are going to be in a single row in our memory. So when we access word 2, okay, our memory pulls that entire row, which includes 0, 1, 2, and 3, and we can then access them in any order. So, I mean, we could go ahead and access 2, then go to 0, then 1, and 3, but that wouldn't make any sense. It's very easy to build hardware that simply starts with 2, then accesses 3, then rolls over to 0 and 1. And so then the idea is that if the processor uh, requests 2, okay, word 2 in this example,
then it can continue executing with that data, okay, and hopefully um, it gets far enough along before it actually needs 3. And so hopefully by the time it actually needs 3 or 0 or 1, they've already been loaded into the cache. And so then we pay the penalty to access the first critical word, the critical word, right, the first word, and then the other ones we don't actually have to wait for. So that's a technique to reduce our miss penalty. Okay? That's critical word first, and it's almost always used. Now, think about instruction access, though. Instruction access is very sequential. So critical word first doesn't work as well on an instruction cache. It works great on a data cache because a data cache, really, only about 30% or so of your instructions are loads. So even if you access data sequentially in an array, there still may be enough instructions sandwiched between your loads to fill out the rest of the cache line before they're needed. But in the case of an instruction cache, you're going to go and you're going to access 2, and then on the following cycle, so then what will happen is you'll request 2, the cache controller will go out and retrieve 2, and then of course in a pipeline fashion, it's also going to be requesting 3, 0, and 1. 2 comes in, it's going to give it to the processor, hand it off to the processor, and then the processor's immediately going to then request 3. And you're like, well, shit, okay, I'm still waiting for 3 from the next memory. So then it stalls, right? Um, and so that's just the way it goes. So again, critical word first doesn't work as well for an instruction cache, but um, now, it could be that if you have a level 1 cache and a level 2 cache, that perhaps you can actually, maybe it takes 3 cycles to access the critical word, and then every word after that is accessed in a cycle. Well, then in that case, you can keep the processor fed with critical word first. You access the first one, and then the next cycle you can then provide the next one, and so on and so forth. Now, of course, if you're accessing sequentially, as soon as you hit this cache block boundary, then you're gonna then have to access the next cache line, right? Okay. So you hit this boundary, and then you're sequentially accessing instructions. So then you're gonna hit this one, and so on and so forth, and then just keep going that way, right? And so that actually brings me to another technique for improving cache performance. I normally spend a lot more time on caching in the graduate class, and so it's on my mind, and I really enjoy it. So I guess I'll just keep going. Notice how on this particular example where we're sequentially fetching instructions, we know that after we access uh, cache block 53, we're going to need 54 and 55. Well, so for one thing that works very well with instruction caches is what's called prefetching. So what a instruction cache oftentimes will do is when you request a cache block, it goes ahead and retrieves not only the cache block um, that was requested, which is called a demand miss, but it does a prefetch miss as well, and it'll go ahead and grab the next block. And you can take that even further with what they call stream buffers, where it really tries to take advantage of the bandwidth in the next level of memory hierarchy, and so you access block 53, and then it goes ahead and requests 54, 55, 56, and however big your stream buffer is. Um, we actually in the graduate class we read a paper on stream buffers, so it's pretty neat. So anyway, there's a lot of different techniques you can do to improve performance, and modern processors are doing everything. They're doing prefetching. They're using critical word first. They're multi-level caches. There's another concept called non-blocking caches that basically allow you to, when you encounter a cache miss, it allows you to still service other requests to the cache. So in our in-order processor, as soon as we encounter a cache miss, the whole pipeline stalls, and so a non-blocking cache makes no sense. But when we start running instructions out of order, when we encounter one cache miss because of a given load word, we might then say, well, what else do you got? And maybe there's a load word that comes after that previous load word in instruction order, but we actually have the data in the cache for that load word. So then we might as well allow it to happen while the cache is filling the previous miss. And there's a couple metrics, which is the number of outstanding misses. And it turns out with a non-blocking cache, you do very well with, 1 to 4 outstanding misses, but then after that, it really doesn't have a lot of benefit. But in a modern i7 processor, you can actually the cache services up to 2 requests per clock cycle, and it's a non-blocking cache. So again, there's a lot of different high performance techniques for caching that we unfortunately just don't have time to talk about here. Let me think if there's any others that are worth talking about. Another advantage of split caches versus unified caches is if you've noticed, as I've talked about level 1 caches, I'll say, oh, well, this technique is beneficial for the data cache, but not so much for the instruction cache, or oh, this technique works really well for an instruction cache, but not so well for a data cache. And so hopefully now you're beginning to see one of the major advantages of a split cache system as opposed to a unified cache system is you can actually custom tune the design of the level 1 cache for the given data stream. So if it's instructions, you put a prefetch buffer, and you can make it a fairly small cache. You can also adjust the associativity. So it turns out that associativity matters less with an instruction cache than it does with a data cache. Okay, so you can get by with an instruction cache. You can get by with a smaller, um, less associative cache. So less complexity there, but then you benefit a lot from a prefetch buffer. So you might add complexity with a prefetch buffer, but it decreases your performance or increase your performance. But then on a data cache, well, you do very well with higher associativity, and you do very well with what's called a victim cache, which when you evict a block, you put it in this victim cache, which is a little bit faster than the next level of cache. You can refill a victim cache in 1 clock cycle, for example, and so it's a way of improving associativity. Um, so anyway, yeah, then you might make your level 1 data cache a little bit bigger than your instruction cache. So a lot of advantages there. Um, so that's another quiz question. What are the advantages of a split cache system? Okay. All right. Well, while you're doing that, you probably can pause the video and whatnot and answer those questions. Let's move on to virtual memory. Okay. Virtual memory is a very interesting, fascinating topic. And it's one of the oldest topics in computer design. Virtual memory was a thing back in the 60s and 70s. I think it was developed in the early 60s. Okay. Maybe even 50s. I don't know. I'll have to go back and look at the history. But the reason virtual memory is so um, old, and goes way back, is because it was trying to cope with very small amounts of main memory. Okay. Nowadays, main memory is very inexpensive, and I mean this little tablet that I bought for $200 came with 8 gigs of RAM. Okay, that's a lot. That's a lot. Um, and a buddy of mine just bought a computer at work that has like 120 gigs of RAM, and the computer I have is expandable up to 600 some gigs of RAM. So that that is a historical problem. So virtual memory solved a historical problem that really doesn't exist too much today, but virtual memory solves so many other problems that it's still very important. Okay, any anytime you want to run an OS, an operating system, your processor more than likely has to support virtual memory. There are ways to get Linux to run on a processor without virtual memory, but it's very painful. Um, Now, that being said, deeply embedded systems are often a different case. Um, you'll have real-time operating systems that don't necessarily need virtual memory. So, little embedded processors like the PIC32, they'll have some sort of memory management, but they won't have a full virtual memory system. Okay. So what the hell is virtual memory? Let's talk about that. Okay. So it was originally developed to cope with small amounts of main memory, allowing data to be swapped between disk and main memory, or primary and versus secondary storage is what they used to call it back in the day. So primary memory being your your RAM, which it wasn't RAM back then. Um, there were different ways of implementing uh, primary memory. Well, I guess it was RAM, but it wasn't SRAM. Okay, one of them was using little magnetic. They look like little donuts, and that's called core memory. And so each one of those little donuts stores 1 bit, and they would magnetize it. Okay, so then if it was magnetized, then it was storing a one. If it was magnetized in the other direction, then it was storing a zero. And that was kind of cool. So again, core memory was very expensive, and secondary storage was on. Well, at that time, it was stored on these giant drums, but it was giant drums, but um, it was still using magnetic disc technology, right? Which is what like your cassette players used, your VHS players used, um, your tape. We literally stored data on big tape reels, okay, um, and um, and so uh, that was our secondary storage. Okay, so it was using magnetism in a way, but like we do with a hard drive. And of course, nowadays, I mean, secondary storage is a lot of times flash, like this tablet that I have for a mobile device. But anyway, so virtual memory was used because we had programs that were too large to fit in our memory space, in our primary memory space. So we had to then have a mechanism that allowed us to swap data between the primary storage and our secondary storage. Okay. Well, nowadays, virtual memory solves a handful of other problems. For one, it allows multiple processes to share resources. So, um, this wasn't an issue back in the 60s, but as we started getting into the 70s and we started having operating systems that then ran multiple programs, once we could run multiple programs on a computer, virtual memory became a necessary tool to do that. So virtual memory allows us to run multiple programs on a single processor. Okay, and it provides a protection mechanism also between the operating system and these programs that we're running. So the virtual memory is what protects the operating system, um, and also what protects a given program from another program. Okay, or program or process. Okay. I have to come over here and turn my swamp cooler on and off because I don't have it controlled with a thermostat, which I started doing a little research on an Arduino board. I'm going to build a little Arduino board that will allow me to connect my swamp cooler up to my thermostat. I've got an ecobee thermostat, and it offends me to have a thermostat to control a separate one to control the heat versus the cool. So I want the ecobee to control both of them. And so I'm going to use an Arduino board to receive output from the ecobee and then control the swamp cooler. Because the ecobee is designed for a refrigerated air system, and swamp coolers require slightly different control. Anyway, random tangent. Hey, if you want to talk more about that, yeah, email me. I could go on for quite a bit of time. But that's an example of how you would a deeply embedded system. There you go. And Arduino uses a Atmega microcontroller, so it's a little 8-bit microcontroller. See, now I tied that into our lecture today. Okay. Um, okay, and that Atmega chip, because it's a deeply embedded microprocessor, will not have a virtual memory system. Okay. Okay, so virtual memory also allows each process or program to have its own virtual view of memory. And you can't see, but I'm doing air quotes when I say virtual. Okay? So we can build or we can write programs as though we have full um, control over the memory, as though the entire memory is all ours. Okay, and each program can be written that way because each program has its own view of virtual memory. Okay, and I want to introduce a term here that's called a process, and you probably have heard that, especially if you go into Task Manager in Windows, or maybe you in Linux you either type in PS in the command line, or you look at you top is another program that allows you to view all of the different processes running on your computer at a given time. And so you may wonder, well, what the hell is a process? Well, a process is basically a program. Okay. Um, I believe you can have programs with multiple processes, um, but for most programs they only have one process. Each process can have multiple threads. Okay. And so each process has its own view of virtual memory. Okay. And yeah, you can have a very complicated program that runs multiple processes because it's maybe a bunch of different individual smaller programs stitched together. For example, like running a script or whatever. Um, but each process has its own view of virtual memory. Okay, and and that and I've got some. Let's move on to some graphics. So I've got some pictures that will explain that. Okay. So if it doesn't make any sense, it will in a minute here. Okay. Real quick, some terminology here. Don't confuse virtual memory with virtual machines. They're a little different. Well, actually, they're quite a bit different. Um, Virtual memory virtualizes just the memory system, whereas a virtual machine virtualizes the entire machine. My Alexa, which is built into the Echo Bee, is like talking to me because it's listening to my lecture and it's thinking that I'm saying something. I don't know. I may have to turn that off. It's telling me it doesn't understand what I'm talking about. Okay. All right. We live in this this electronic age where we've got devices listening to everything we're saying. Although you probably aren't listening to me, you're probably drowning it out, so Alexa's the only one listening to my lecture. But she's confused, so okay. All right. So virtual machines, well, the way I look at it is virtual machines sort of take this virtualization to a whole new level, and they actually virtualize the entire machine or processor. Well, I mean, yeah, it's actually the whole computer system. So, of course, virtual machines are very, very useful. I use a virtual machine on a daily basis. So, for example, I do things that require me to interact with Linux, Windows, and Mac systems. So, I have a MacBook with a Windows virtual machine on it. And so, because right now I'm working on a Windows software development environment for my um, processor, for the PEEP microprocessor, so I'm working on a Windows development environment for software developers that's based on Eclipse. So I have a Windows virtual machine that I run that in. Okay, and so that Windows operating system thinks that it is the sole operating system on that machine, but actually the host machine is the MacBook the Mac OS is the host operating system, and it's hosting this virtual machine that is then running Windows inside of it. Okay, and servers use virtual machines all the time because they provide very good compartmentalization. And actually, that's when you talk about cloud computing, they're using virtual machines. So when you go and you lease some computation time on a cloud server, like an Amazon cloud server, um, they're going to give you a virtual machine. You'll have a virtual machine, and they'll have a server, this giant server that's running, dozens of virtual machines. Okay, or actually, it might be a warehouse scale sized computer system that's running thousands of virtual machines. Honestly, um, so you get into the data center sizes of things. Um, okay, so that's a tangent. I just want you to realize that those are two separate things. Um, virtual machines, like it's very common to have a computer nowadays that is not running a virtual machine. Like my tablet, it's running the Windows operating system and nothing else. Okay. Um, all right, but it is running virtual memory. Okay. Okay. Um, with virtual memory, we have physical address space and virtual address space. Okay, the physical address space is the actual physical memory, so it's your RAM, and the virtual address space is the address space that your program sees. Okay, and there's a translation between virtual and physical address space that happens under the hood in a virtual memory system. Okay. Um, Now, if you have it gets even more complicated when you have a virtual machine that's running virtual memory. Now you've got three types of memory. You have virtual memory, you have physical memory, and then between those two, you have, I think they call it real memory, if I remember right. Okay, so had a little bit of interruption because I wanted to check to make sure the video was running, and I wanted to verify that I was saying the right things. And yes, it is. It is in fact real memory that sits between virtual memory and physical memory in a uh, virtual machine that's implementing virtual memory. So the physical memory is still the RAM. Okay, but the real memory now is the memory of the host processor, okay, the virtual memory of the host processor. Because what's interesting is the I probably should explain what virtual memory is a little bit more because I'm getting quite a bit ahead of myself. But your virtual machine, like the example I was giving, where it was a Windows virtual machine that's running on the Mac OS, that virtual machine is running within the Mac OS's virtual memory. Okay, so that virtual memory that it's running within is actually the intermediate real memory. Okay, let's move on before I really confuse you. See, the problem is I can't see your deer in the headlights expressions as I'm explaining this stuff. Okay, I also realized when I paused the video is that I don't have a lot of time left in this lecture, so let's keep moving forward. Okay, so what does virtual memory do? Virtual memory provides an automatic mapping from virtual addresses of a program to the physical addresses of the machine. Okay, so again, every program has a process, and that process has its own view of virtual memory. And so when we're running a program, we're constantly doing this translation, address translation. Okay, and I've got some diagrams. Boy, I hope they come quickly because I'm really struggling to explain this right now. Okay. Um, Each virtual address space up is broken up into what are called pages, and a typical page size is 4 kilobytes. Okay, and on the physical memory, it can be located anywhere in physical memory, or it can even be located on disk. Because remember, the original um, goal of virtual memory was to allow us to run programs that required more memory than we actually had. So required more virtual memory than physical memory. Okay, so that means that some of these pages would be stored on disk. Okay, and yeah, so storing pages, yeah, exactly. That's the third bullet point. Storing pages on disk allows a program's virtual space to be larger than the physical address space. Okay, and nowadays, of course, what we have so much physical memory that really what we what we use virtual memory for is to allow us to run multiple processes or multiple programs. I mean, if you open up your task manager and look at all of the processes running, I mean, you're going to see hundreds of processes running at a given time, even on a very simple machine. Okay, so there's that diagram we desperately need. Okay. So again, every virtual address space is broken up into these pages, and 4 kilobytes is pretty standard for a page size. So each of these are 4 kilobyte pages. And what's interesting is, although they're in order in our virtual address space, they can be stored anywhere in physical address space. Okay, and they can even be stored on disk. Okay, so if we and notice in this example, our virtual address space is smaller than our physical address space, which means that if we're using this entire virtual address space, then some of these pages have to be stored on disk. And that was definitely the case for the early days of virtual memory. Okay. Nowadays, what's interesting is we have very large virtual address spaces, but they're very sparsely used. Okay. So what's neat about virtual memory is um, you can have a very large virtual address space, but only the pages that you use are actually going to consume space in the physical uh, memory. Okay, and so I mean, like for a 32-bit processor, each process has uh, 2 gigabytes of user space. Okay, and you may say, well, wait a minute, 32 bits, 2 to the 32 is actually 4 gigabytes, and you're right. Um, but 2 of those gigabytes of that virtual address space is allocated to the kernel. Okay, and so hopefully I'll have some time to talk about address spaces a little bit more. Um, Actually, wait. Well, let's talk about it now. Let's go to a virtual whiteboard here. Okay. So if we have a 4 gigabyte address space, okay, we immediately cut it in half. Whoops. And the top half is the kernel space, and the lower half is the user space. Okay. Now within the kernel space, we actually further subdivide our 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 address space. There's different sections in kernel space, and like for example, we have a section in kernel space that holds uncached memory. That's where your memory mapped I/O goes because you don't want to run, uh, you don't want to access I/O devices through a cache. You access them directly. And there's also a section of kernel space that's unmapped, but it's cached. And unmapped means that it doesn't use virtual memory. Now, and that's what's interesting is in there's another section in kernel space that's cached and mapped, which means in kernel space the kernel uses virtual memory itself. Okay. Now we can have multiple user spaces. Okay, and each user space is dedicated to a given process. Okay. So on the left is process zero's view of memory. On the right is process one's view of memory. And what's interesting is they both have the same kernel view because there's only one kernel. So the kernel space is the same. Every process has the same view of the kernel space, but then what's different is the user space. Okay. Okay. We'll come back to that in a little bit. So hold that thought. Okay, so again, the main concept that I'm trying to get through right now is that we divide our virtual address space up into 4 kilobyte pages, and those pages, although they're in order in our virtual address space, they can actually be stored in any order in the physical address space. Okay. So what that lends itself nicely to now is now we can support multiple processes. Okay. And they can all be jumbled up into the same um, physical address space. And I'm looking here to see if I have a diagram of that. I should. I'm not finding one. Why do I not have a diagram of that? That's a very important concept of virtual memory. Huh. Weird. Okay, we're going to have to draw that. Okay, because this is important. Um, let's go to another blank sheet. Okay. So here's our physical memory. Here is user space 0, user space 1, and so on and so forth. Actually, let's just do a dot 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 and then make this n. Okay? And each of these spaces is divided into pages. This is really a bad drawing. It gets worse as the night goes on. Ooh. Okay. And again, these are all mapped to different locations in physical address space. Now, the operating system is what maintains the virtual memory system. So the operating system has algorithms that, placement algorithms that decide, that strategize. Oh, now what I'm not showing here, which I really do need to show, is how they can be intertwined. Look at that. Uh-huh. Okay. So that virtual memory allows us to now have multiple processes. In this case, we have n plus 1 processes, which has allows us, which means we have n plus 1 views of user space, and then the kernel space is also mixed in here. And each process sees its user space in its user space in a nice in order fashion, but in physical memory, which is here, physical memory, all the pages can be stored in all kinds of different locations. It's time for a quiz, so describe the benefits of virtual memory. Okay. And I honestly think we're out of time, so we'll pick back up here next time. Hopefully, I've had a little bit more rest before that, and yeah, and we'll talk more about virtual memory when we come back next time. We'll go over these slides here. This is a very fun topic. Well, I hope everybody's healthy and happy, and we'll talk to you next time.